So today we're going to discuss exponential functions. So we have three basic goals for today, and one is to graph and apply exponential functions, and that includes both growth functions and decay functions. We're going to look at what a horizontal asymptote is and how do we identify them. And then we're going to look a little bit at comparing the function transformations when it's applied to an exponential function. So what is an exponential function? Well, if I have a positive real number b and I have a function in the form of b to the power of x, then that is an exponential function. B is the base of the function, and it's going to be, it can be a fraction, it can be a decimal, but it's going to be a positive real number. And then I have a variable x, which is going to be my exponent. So you can see from this graphic that there are actually two types of exponential functions. One type, as your input increases, the output actually decreases. That's called exponential decay. And we'll talk about that in a minute. But we're going to start by discussing the exponential growth. And that type of function increases as your input increases. And so exponential growth, what does that look like? Well, we can identify it from the graph. So if you graph it, it will look like this graphic. But we can also identify it in the function itself. When I look at y equals b to the power of x, that base value b is going to be a number that is larger than 1. It's going to be a positive number that is larger than 1. So it might look something like 1.05 to the x power. 1.05 is a number that is larger than 1, so it would be growing. We also might have an integer value. We might have something like 2 to the x. You see that a lot. Something that is doubling. Oftentimes it has a initial value, a factor that's out front, like 100 times 2 to the power of x. Sometimes we also see things like this. We might have something like y equals 5 times 3 to the 2x. And that's somebody made a decision to write the exponent in that manner. It is a choice, though, and we could rewrite it without that factor in the exponent. So we know from our exponent rules the other day that we could write this as 3 squared to the x power. And so this would be the equivalent of saying 5 times 3 squared is 9 to the x power. And so we, instead of writing it as a base 3, we could write it as base 9. But again, that would be a growth, exponential growth. So what about exponential decay? And we can see exponential decay is decreasing here. And what happens is that the b value, when we have this exponential function b to the x, the b value it's still going to be a positive number, but it's going to be a number that is between 0 and 1. So it's going to be less than 1 but greater than 0. So it might be something like y equals 0.85 to the x power. So we can see that we can write the number that is less than 1 as the base. It can be written as a decimal. Oftentimes we see it written as a fraction. So we could see a base of 1/2 to the power of x. Again, that is a positive number that is smaller than 1. So that is one way to write an exponential decay function. But we have to be careful. We can always change this so that this number is not less than 1 by changing the exponent to a negative. So remember from our exponent rules, when I have something like 1/2, I can rewrite that as this would be the equivalent of 2 to the minus 1 to the x power. And so in that way, if we use that little exponent trick, we can write it as 2 to the minus x, because the exponent rule says that I can multiply these. So there are two basic forms that we'll see in the equation. You'll see a positive base that is smaller than 1, like a fraction or a decimal smaller than 1, a fraction that is less than 1. Or we could see something like this with a positive base that is bigger than 1, but it's going to have a negative exponent. So if it has a negative exponent, or if it has a base that is smaller than 1 and a positive exponent, then you're going to have a decay function. And that kind of function is going to decrease in value as your input increases. So let's graph a simple exponential function, y equals 2 to the x. Whenever we graph, a real key point is, as always, the y-intercept. And so if I put in 0, I should get my y-intercept, because by definition, the y-intercept is when your input is 0, when x is 0. So I have 0, and 2 to the 0 power is going to be 1. And so this point, 0, 1, in this case, the y-intercept is an important point for exponential functions. As I increase from there, if I have 1, 2 to the 1 power would be 2, 2 to the 2 power would be 4, 2 to the 3 power would be 8, and so I'm doubling each time, and so we'd have 2 to the 1, and then 2 to the second power, 1, 2, 3, 4, and then the next one would be 8. Now it's interesting to look at what happens as you get a negative exponent. So if I have negative 1, remember 2 to the minus 1, that's 1 over 2 to the 1, 1/2. So as I move backwards, I'm actually going to be in this direction. As I increase, I'm doubling. But if I go the other way, I'm going to be taking half each time. And so half of a half is going to be 1/4. And to the negative 3, that's going to be 1/8, 1 over 2 to the third power. And what you can see is happening on the left side is that I'm getting closer and closer to 0, but I'm never going to actually get to 0, because I can never multiply by a positive, in this case, fraction, and get an answer of 0. And so our graph is going to look like this. It's going to be it's going to go like this. But what is very clear is that I never actually reach this value of 0. And so this line in green, in this case the x-axis, is called the asymptote. And an asymptote is a value that the function approaches but never reaches. And this one is a horizontal asymptote, because of course it's a horizontal line. And horizontal asymptotes are a feature of exponential functions, and they help us to graph them. So how do transformations work with exponential functions? Well, they work the same way that when we discussed other function transformations. And we can see here that in this particular function, I'm going to compare it to the parent function of y equals 2 to the x. And what changes would I expect from this transformation? Well, I can see that the input, has become x minus 3. So that's going to tell me that my graph is going to shift 3 units to the right. And I can also see that I'm adding 3 on the outside to the output, and so my function is going to shift 3 units up. And what can help us when we graph this is, one, the idea of that horizontal asymptote. I know that the original horizontal asymptote is going to be at the value of y equals 0, the x-axis. Now, because this is shifted 3 units up, I know my new horizontal asymptote is going to be at the point value y equals 3, because it's 3 higher. And so the original asymptote was here. The new one is going to be at y equals 3. And you can see by the graph where we've graphed that the red function, which is the new one, has shifted 3 units up. What else is happening? Well, those key points we can look at. So in the original function, y equals 2 to the x, a key point would be the value of 0, 1, So when I put 0 in, 2 to the 0 is 1. Also, when I put 1 in, 2 to the 1 is going to be 2. Well, those points are now going to change, and how will they change? Well, I'm adding 3 to the input and to the output. So 0, 1 is now going to be 3, 4, and 1, 2 is going to be 4, 5. And so the point 0, 0, 1 has now become 3, 1, 2, 3, 4 right here, and 4, 5 is the second point. And so the original points were 0, 1 and 1, 2. And that will help me get an idea of what the graph would look like. So in economics, we often talk about inflation. And inflation is the idea that if I buy something this year, it's going to cost me less than if I buy it next year because prices go up. And so they predict inflation based on percents. And in this case, we're saying that in a particular period of time, the inflation was 4% per year for each year from 2012 to 2025. And we're going to look at what happens to something that would cost $10,000. And so think about this. So in 2012, that's the first year, whatever I'm going to buy would cost $10,000. Then in 2013, it's going to cost $10,000 plus $10,000 times 0.04. That's that 4%. Well, a shorthand way of writing this is just 10,000 times 1.04. And so you can think of it as 10,000 plus 10,000 times 0.04, or just 10,000 times 1.04. And this latter way is the easiest way for us to write an equation. And so in 2014, how would this change? Well, I'm going to take what my value was in 2013, and I'm going to multiply it by 1.04 again. So this would be $10,000 times 1.04 times 1.04. And so I'm going to have 10,000 times 1.04 squared. So 2014 is 2 years from 2012, so it's squared. 2013 is 1 year from 2012, so it's 1.04 to the first power. And so our equation for this would simply be y equals our starting value, our initial value of $10,000 times the growth factor of 1.04 to the x, or the t. We'll call it, it's defined as t here. And t is the number of years after we started counting, which is 2012. So suppose that we want to graph this function from t equals 0 to t equals 13. Well, we would use our graphing calculator. So if we want to graph this using our graphing calculator, we're going to put in the equation into our y menu. So here I have y1 equals 10,000 times 1.04 to the power of x. And how would you choose your window? Well, we know this is a growth function because this base of the exponent is greater than 1. And we also know the starting value, that initial value would be 10,000. So this y-intercept here is going to be 0, 10,000. So I know that my window has to go higher than that. And so you're going to make a educated guess for where to start. And I did my x from 0 or negative 10 to 20, and my y window from negative 10 to 20,000. And here you can see that we got a reasonable graph. So how would we use technology to solve the problem if we wanted to know what would the cost be in the year 2025? Well, one way is to use our graphing calculator, and we put our graph in. So here's our original graph. And if I hit the trace function, so I hit trace, and then I type in 13, I'm going to get the output for that value. Now, why did I use 13? Because I'm looking in 2025. So how many years is it past the year 2012, which was the starting value? Remember, this is the year 2012, 0. So I need to find an input for 2025. Well, that's 13 years after that. So I need to find this this output for the year 2025. And so that's going to happen when x is 13 or t equals 13. And that turns out to be 16,650 0.735. So 16,650 and 74 cents is what that would be exactly. You could also see this by looking at your table. 2012. So we might also ask you, in what year would the cost of this item reach 15,000? So this is different from the last question in that they are giving you the output of 15,000 and you have to find the input. What year would that happen? And a very convenient way to do that is to put in your Y menu the horizontal line y equals 15,000. And then when you graph that on top of the original graph, you can find that point of intersection. And we can see that they intersect at x equals 10.3 and y equals 15,000, of course. And so that would mean that it's about 10 years after 2012 when that would happen. And so that would be the year 2022. But you can see by the 0.3, it's a little bit longer than that. So a better answer would be between 2022 and 2023. So let's talk about exponential decay functions. So an exponential decay function would look something like this. And what would the equation look like? So the equation is going to have, well, there's two forms. One might look something like 2 to the minus x, but it also could look like the equivalent form of this would be 1 over 2 to the x. So there are two ways that we write exponential decay and recognize it. One, if it has a base that is a positive number that is greater than 1, it's going to have a negative exponent. The other way is if it has a base that is a positive fraction between 0 and 1, then it's going to have a positive exponent. So those are the two ways that you will see exponential decay. Now, remember, the difference was that if I was looking at growth, this number would be a number that is greater than 1. So that is the best way to distinguish it. But you got to be careful because, as pointed out, this number is also greater than 1, but the exponent is negative. So that sort of accounts for the fact that it's not growth, it's decay. So now we're going to look at an application of exponential decay. So it says it pays to advertise, and it's frequently true that weekly sales will drop rapidly for many products after an advertising campaign ends. This decline in sales is called sales decay. Suppose that the decay in sales of a product is given by the equation S equals 1,000 times 2 to the negative 0.5x dollars, where x is the number of weeks after the end of the sales campaign. And then we want to answer some questions about it. So the idea is that when you're advertising, people are thinking about your product. Once you stop advertising, fewer and fewer people are going to think about it, and the longer since you placed your advertisement, the fewer the people that are thinking about it. And apparently this change happens in an exponential decay way. So the first question they ask is, what would be the level of sales when we stopped our advertising campaign? So it's important to look at how we define the variables. X is the number of weeks after the end of the sales campaign. So when the sales campaign just ended, X is going to be 0. And so this one is fairly easy to do because we put in 0 for the exponent, So 0 times negative 0.5, that's 0. And so this is just going to be S equals 1,000 times 2 to the 0 power. Well, we know 2 to the 0 power is 1, so this is going to be $1,000. So that means they were selling $1,000 a week of product when their advertising was fresh in everybody's minds. The next question they ask is, what is the level of sales 1 week after the end of the campaign? So 1 week after the end of the campaign, that's saying X is equal to 1. And so there are a couple ways. One, if you graph this on your calculator, we can just type in, hit trace, and then type in X equals 1. So type 1, enter. And you can see that that would be $707 about in 11 cents, I guess, but about $707. And then another way you could look at your table, if you had that function in there, go to X equals 1, and you have $707. Of course, it would also be suitable to just put, 1,000 times 2 to the power of negative 0.5 times 1, which is negative 0.5, and that would also be equal to 707.1 about. So you can see that after 1 week, the sales have dropped all the way down to $707. The last question they're going to ask us about this sales decay was, use a graph of the function to estimate the week in which sales were equal to $500. So $500, that's half the original value. So that would give you a sense of when you might want to start advertising again, is how fast your sales are dropping. And so we have the easiest way to do this is to simply use your graphing calculator, and we have our original function in the calculator, and you can see on the graph here that here's the original function. And then go in and put in the equation y equals 500, and that's that horizontal line right here. And where their point of intersection is the value where s is equal to 500. And so that's going to be right here. And if you use the second calculate intersect, you can find that that's going to be at x equals 2. So at 2 weeks, apparently the sales have dropped by half. Now, will this ever, according to this model, will the sales ever fall to 0? In real life, the sales could certainly fall to 0. But in this model, you can see that there's this horizontal asymptote at y equals 0. And so no, the sales are never actually going to get to 0 in this model, because exponential graphs, they can get close to the 0 value, but they're never going to get to be exactly 0. And so the answer would be no. That's a deficiency in the model. But remember, models are not real life. We're using them to represent models, but we have to think about them as well. So I'd like to introduce you to a very special number called the number e. I want you to think of this number as being like the number pi, in that it's irrational, and anytime you write it down, you're going to be truncating off a lot of it. And you're just going to pick however many digits you need for the specific purpose that you're using the number for. It's a number that's come up again and again in mathematics, and finally mathematicians, decided, hey, we're seeing this number everywhere. It must be a real important number in the universe. And we're going to use it when we do logarithms, because it's very common to use the logarithm's base e. It's called the natural logarithm. If you want to get this on your calculator, this function, you're going to press the second button, and then you're going to look for the ln button. And then when you do that, it's going to come up e to the x. And so you could put in the number 1 and then enter, and it's going to give you 2.718 ... etc. So I'd like you to try that on your calculator and see that works for you. If you have difficulties using it, let me know, and I will make a little video showing you how to do that. So one application of this number e, where it appears, is when you're investing and you're looking at interest that is compounded continuously. In this equation, S is called your future value. It's how much money you take out of your account when you end your investment. And hopefully it's higher than the amount that you put in, which was your principal, P. And then remember, the number E is not a variable, and you would get it on your calculator by pressing second ln, and that would bring up e to the x. And so you're going to type in, for the x, you would type in your interest rate, R, which would be your rate would be as a decimal, so we'd type in 0.12 here. So it's your interest rate as a decimal. In this case, our principal was $10,000. And the last part we're gonna have is our number of years. So in this case, T would be 15 years. So we could put this in our calculator as 10,000 e to the 0.12 times 15, and we should get our answer. A way I like better is if we put it in our Y menu. And so here we put it in 10,000 e to the 0.12x. And then we can graph it. Notice that the value starts at 10,000, so it's going to have to go much higher. So you might have to play a little bit with your Y max. Probably like 100,000 or something like that would be suitable. And then you graph it. So here's my function. I'm interested in what the value is when x is 15. So I'm going to hit trace, and then I'm going to type in 15, enter, and you can see my answer is $60,496. You also could, once you have this graph, you could look on your table. And you got to be careful about your table, though. It depends on how much information you want. If you just need to know that it's about $60,500, the table would be perfectly fine. If you were interested in the cents that you have, the 0.48 cents, your table's not going to show you that unless you did an adjustment to the number of decimal places.